The messages and channels model of messaging is a great abstraction and a good way to design a service's asynchronous API. But in order to implement a service, you need to choose a messaging technology and determine how to implement your design using its capabilities. So let's have an idea on what I'm talking about. Messaging-based applications typically use a message broker, an infrastructure service through which the service communicates. But a broker-based architecture isn't the only messaging architecture. You can also use a Brokerless-based messaging architecture in which the services communicate with one another directly. The two approaches have different trade-offs, but usually broker-based architecture is the better approach. In a Brokerless architecture, services can exchange messages directly. ZeroMQ is a popular Brokerless messaging technology. It is both a specification and a set of libraries for different languages. It supports a variety of transports, including TCP, Unix-style domain sockets, and multicast. The Brokerless architecture has some benefits. It allows lighter network traffic and better latency because messages go directly from the sender to the receiver instead of having to go from the sender to the message broker and from there to the receiver. It eliminates the possibility of the message broker being a performance bottleneck or a single point of failure. It features less operational complexity because there is no message broker to set up and maintain. As appealing as these benefits may seem, brokerless messaging has significant drawbacks. Services need to know about each other's locations and must therefore use one of the discovery mechanisms described earlier in the service discovery video. It offers reduced availability because both the sender and the receiver of a message must be available while the message is being exchanged. In fact, these drawbacks are the same as when using synchronous request-response interaction style. Because of these limitations, most enterprise applications use a message broker-based architecture. A message broker is an intermediary through which all messages flow. A sender writes the message to the message broker, and the message broker delivers it to the receiver. An important benefit of using a message broker is that the sender doesn't need to know the network location of the consumer. Another benefit is that a message broker buffers messages until the consumer is able to process them. There are many message brokers to choose from. Examples of popular open source message brokers include ActiveMQ, RabbitMQ, and Apache Kafka. To mention that there are also cloud-based messaging services such as AWS SQS, SNS, Kinesis, and so on. When selecting a message broker, you have various factors to consider. This includes the supported programming languages. You probably should pick one that supports a variety of programming languages. The second one is the supported messaging standards. Or does the message broker support any standards such as AMQP and STOMP, or it is proprietary? The third one is messaging ordering. Does the message broker preserve ordering of messages? The next one is delivery guarantees, or what kind of delivery guarantees does the broker make? Then we have to look to the persistence. Are messages persisted to disk and able to survive broker crashes? Then we have to look to the durability. If a consumer reconnects to the message broker, will it receive the messages that were sent while it was disconnected? Then the scalability, or how scalable is the message broker? The latency, what is the end-to-end latency? And the comparing consumers. Does the message broker support comparing consumers? At the end, I can say that it is very difficult to find the perfect message broker that ensures all these requirements. It's a matter of finding a balance between, since each broker makes different trade-offs. For example, a very low latency broker might not preserve ordering, make no guarantees to deliver messages, and only store messages in memory. A messaging broker that guarantees delivery and reliably stores messages on disk will probably have higher latency. Which kind of message broker is the best fit depends on your application's requirements. It's even possible that different parts of your application will have different messaging requirements. Each message broker implements the message channel concept in a different way. As this table shows, GMS-based brokers such as ActiveMQ have queues and topics. EMQP-based message brokers such as RabbitMQ have exchanges and queues. Apache Kafka has topics, AWS Kinesis has streams, SQS has only queues, and SNS has only topics. Almost all the message brokers described here support both point-to-point and publish subscribe channels. The exception are SQS, which only supports point-to-point, and SNS strictly dedicated to pub-sub channels. Practically speaking, a service needs to use a library to send and receive messages. One approach is to use the message broker's client library, but a better approach is to use a higher-level library or framework that hides the low-level details and directly supports the higher-level interaction styles. There are many advantages to using broker-based messaging. The first one is loose coupling. A client makes a request by simply sending a message to the appropriate channel. The client is completely unaware of the service instances. It doesn't need to use a discovery mechanism to determine the location of a service instance. The second benefit is message buffering. The message broker buffers messages until they can be processed. With the synchronous request response protocol such as HTTP, both the client and service must be available for the duration of the exchange. With messaging, though, messages will queue up until they can be processed by the consumer. This means, for example, that an online store can accept orders from customers even when the order fulfillment system is slow or unavailable. The messages will simply queue up until they can be processed. 3. Flexible communication. Messaging supports all the interaction styles described earlier. And the last benefit is explicit inter-process communication. RPC-based mechanism attempts to make invoking a remote service look the same as calling a local service. But due to the laws of physics and the possibility of partial failure, they are in fact quite different. Messaging makes these differences very explicit, so developers aren't lulled into a false sense of security. On the other hand, there are some downsides to using messaging. The first one is potential performance bottleneck. There is a risk that the message broker could be a performance bottleneck. Fortunately, many modern message brokers are designed to be highly scalable. The second one is potential single point of failure. It is essential that the message broker is highly available. Otherwise, system reliability will be impacted. Fortunately, most modern brokers have been designed to be highly available. And the last downside is additional operational complexity. The messaging system is yet another system component that must be installed, configured, and operated.